All right, so swap x and y in the problem. So we're going to have x equals 2y plus 1 over y minus 1. So everywhere there was an x on the other side, I put a y, and everywhere there was a y, I put an x. And we got to get y by itself again. Uh-oh. There's more than one y in there. That means I got to get them together at some point here. So what would be your first step in trying to get y by itself here? I think get that y out of the denominator would be a good start. Because it being in the denominator is a big problem. That's what makes it tough to do. It makes it look weird too. So we're going to kind of make it a little less weird. So xy minus x equals 2y plus 1. All right, so if I'm trying to get y by itself again, what needs to be on the same side? Things that have y, right? And then the other side needs to be the stuff that doesn't have a y, okay? So I've got two things that have y. I've got xy and 2y. So I need to get those on the same side and get the other stuff that doesn't have a y on the other side. So I'm going to do that math. I'm going to add x and subtract 2y. So that's xy minus 2y equals x plus 1. Now, I got everything that's got y's on the side, but there's an x mixed in there. What can I do to this side that would maybe get y separated? Think about something you learned in Algebra 1. What'd you say, Either? Can't really divide by y, but it's kind of the same idea. Greatest common factor of y, which is kind of the same thing as divided by y. But if I factor out a y here, that's going to give me x minus 2 in the parentheses. And then what's going on between y and the x minus 2? They're multiplying, and the opposite of that would be, what am I going to divide by to leave y by itself? I'm going to divide by this x minus 2. There's y equals x plus 1 over x minus 2. In function notation, f inverse of x plus 1 over x minus 2. What do I need to tell it about the domain? Positive 2. And there's our inverse function. That step right there, going from those, between those two steps, that transition is the key. So you got to figure, anytime you've got a rational function to start with, you're going to have to do that. Okay. So know if it's a rational function when you start, you got to do this factoring jig here. Okay. So that's, keep that in mind as you're going through this. Let's do this one. G of x is equal to x squared, where x is greater than or equal to 0. Now this is important for this problem because what do we know about the x squared function? It's a parabola, right? It normally looks like that. But would that pass the horizontal line test? No, but it passes the vertical line test, but it doesn't pass the horizontal. So this x is greater than or equal to 0. What it does is it says, oh, you're only doing this side of the parabola, which now that will pass the horizontal line test. That's what that does for the problem. That domain restriction that they put on it. It makes it 1-to-1. Because of this domain restriction, it becomes a 1-to-1. If it doesn't have, if it has less than or equal to 0, that's still 1-to-1. But if it doesn't have this kind of thing on here, it's not a 1-to-1 function because it wouldn't pass the horizontal line test without this. This is what makes it 1 to 1. Just having that on there. Okay. Now we're gonna find the inverse of that. So again, that g of x is the same thing as y. We're gonna swap x and y. This one seems pretty easy, right? What do I do? Okay. And if I put a square root into the problem, what do I have to put in front of it? Plus or minus. So we get y is equal to plus or minus the square root of x. Which one is it for the inverse? Why is it going to be the plus side and not the minus side? Yeah, the inequality up here was greater than 0, so we're going to use the plus side of that. If it were less than or equal to 0 up here, we would use the minus side of that. We're getting negative x's, right? So here we're going to use the positive side because the inequality at the beginning was positive side. If this were the negative side, we'd use the negative side. We'd use minus square root of x. Kind of simple, but little trick to it that you got to just keep in mind. Look at that inequality. That's an important part of that one. So we got to be careful of that. All right. Okay. So we found several inverses here. We kind of get the idea here. You swap, interchange x and y, and then solve for y again. That's the whole idea of finding an inverse. Now, one of the things that we do in this section is we verify inverses. All right, so we'll do an algebraic verification first. The way verification of inverses, if they give you two functions and they say, are these inverses of one another? You can algebraically decide that by doing function composition. So if f of x and g of x are inverse functions, then the composition f composed with g of x is going to equal x when you simplify it out. Just plain old x, nothing else. Can't be negative 1x, can't be a half x. It's got to be just plain x if you do that composition and simplify it. And the other direction, g composed with f of x, is also equal to plain x. It works in both directions. Okay? The composition works in both directions. So if you're asked to verify if two functions are inverses of one another, then you're going to do function composition in both directions with those two functions. Okay, so let's look at a pretty easy one here. Example E, are these inverse functions? F of x is equal to 2x plus 3. G of x equals 1/2 x minus 3. Okay. So this is the I guess in geometry you did proofs. This would be the proof of inverses. Finding the inverse is not proof. Function composition is proof. It's a stronger operation. So let's do the f composed with g of x. So what does that mean we do? Yeah, so 2 parentheses 1/2 x minus 3 and plus 3 on the outside. It's all multiplication in this first little part here. So I'm just going to multiply 2 times 1/2 and get rid of that fraction. 2 times 1/2 is 1, right? So it's going to be 1 times x minus 3 plus 3. So that's going to be x minus 3 plus 3, which is x. So f composed with g of x is equal to x. We verified it in one direction. We got to verify it in the other direction. Okay. So we're going to do g composed with f of x. So for this one, we're going to take the f of x function and plug it into the g of x function. So it's going to be 1/2 parentheses 2x plus 3 minus 3. From there. Hey, bro. And then multiply, or I'm going to simplify the inside there. Those cancel each other out. 1/2 times 2x. Half of 2x is x. G composed with f of x is x. It verifies in both directions. So f of x and g of x are inverses. This is the proof that it is using that composition. Okay. Yes, sir. If they are inverses, they should come out. Both of them should come out to be plain x. If you do this direction and it comes out as negative x, check your signs and make sure you didn't do something wrong there. And then if you try the other direction and it comes out as something else, then they're definitely not inverses of one another. Okay? They both have to equal plain x for them to be inverses of one another. So an algebraic verification is function composition. Okay? Graphically, it's a little harder to see sometimes, but there is a graphic verification. So graphically, inverses reflect across y equals x. So if we looked at these two, if we graph them on the graphing calculator, I'm going to graph y1 is the 2x plus 3. And then y2, I'm going to do the 1/2 x minus parentheses x minus 3. And then I'm going to graph on y3, I'm going to graph y equals x. So we can see that reflection line. There's the first one. There's the second one. There's the reflection line. And we see that this blue one reflects directly across that to get the red one. That's that reflection. So graphically, they reflect across the y equals x line. With linear ones, that's pretty easy to see. When it gets into the rational ones or some of the cubics and things like that, that's a little tougher to see out of that. But algebraically, I think the more complex functions are easier to do, and because once you spread that graph out so far, it's kind of hard to look at the reflection out of it. Once the graph gets doing a lot of twists and turns and things in there, especially when it starts getting those asymptotes going in there with the rational function. So the algebraic verification is stronger, I think, than the graphical verification. I'm gonna ask you to do the algebraic anyway on the quiz and stuff. So you got to show me the both directions there. All right. If you were to do a graph or a algebraic inverse verification, and the first one, and you did all your signs right, and you know you didn't make a mistake, and it's something besides plain x, then you don't have to do the other side to show me that it's not. If you didn't make a sign mistake here, and it comes out to be like 3x or x minus 7, something like that, anything other than plain x, then it's not, they're not inverses of one another. You got to figure most of them are going to be inverses on the practice, because that's what we're trying to get you to learn to do, is verify that they are inverses of one another. So it's just that algebraically, function composition, both directions. Graphically, y equals x line. What I usually do is look at it graphically to kind of know whether or not I should get x when I do the algebraic. If I look at it and I'm not sure, then I'm going to do the algebraic anyway. But if I look at it and I see that, it makes me feel a lot better when I get the algebraic one done and I get X on both of them, because I can see it in both directions there. So algebraically is the way I want you to focus on it, but it's going to ask you, it may give you a graph in the practice that says, are these inverses one another? It'll have two functions drawn. You're supposed to look at the y equals x, y, and see if it reflects. That's how because you don't have an equation. So the practice for this is page 415, 11 through 95. Just pick some of those out of there to get ready for this.